After some work, we have now finally found the fictitious forces in a rotating reference frame. And if you write down Newton's second law, you can see that there are two of them, two distinct terms. The first is the Coriolis force. We're going to deal with that in the next video. Here we're going to talk about the centrifugal force, as the headline here, the title indicates. In spite of looking complicated, the centrifugal force is actually less complex to deal with, and less easier to understand than the Coriolis force. The reason for that is twofold. First of all, the Coriolis force depends on the velocity of an object in the rotating frame. So an object that's stationary in the rotating frame doesn't experience any Coriolis force. Second, even though this is a double cross product, we can actually interpret what it means relatively easily. Here is a rotating object. We have this point P here, and it's moving in the non-rotating reference frame by some velocity v due to the rotation here. And we can show, in fact we showed a couple of videos ago, that this velocity here, v, is just omega cross r. Right, that's what that velocity is. Well, that's what's in here, inside the centrifugal force term. So we can write that the centrifugal force is just mv cross omega. The magnitude of this velocity is going to be omega times the component of the r that's perpendicular to omega. In other words, it is omega rho, and it is in the phi hat direction, tangential to the rotation. Omega is of course omega z hat. That is perpendicular to v. So that also makes it relatively simple to calculate what the centrifugal force is equal to. It is m times rho omega, that's v, that's mv, and then we multiply that by omega, then it's phi hat cross z hat, so that's m rho omega squared rho hat. In other words, it's in the outward direction. So if we use the color blue to code it, then it's pointing in the outward direction, away from the axis. That's hard to see what it says. Okay, so F centrifugal, and that points outward. That's not so surprising. Centrifugal means center fleeing. So it has this form here. We can rewrite it, if we like, also in terms of the velocity as m capital V squared over rho times rho hat. You have probably seen this before in a different context in intro physics, intro mechanics, or then it probably looked like mr omega squared, and it had the opposite sign. We can see, in fact, here that this, the centrifugal force, is minus the centripetal force. So F centrifugal equals minus F centripetal force. Okay, that is not so strange if you think about it. If we look here at a merry-go-round, see if we can fit everything in here. On this merry-go-round, if we look first in the inertial frame of reference, that's S naught. There is a centripetal force that makes you, if you follow around the rotation of this merry-go-round, that makes you move in a circle. If the net force on this horse were 0, then it would go in a straight line straight off the merry-go-round. So there's a net centripetal force. In the rotating frame of reference, the horse is stationary. There's no acceleration on it. So what we have to have then is the net force, if Newton's law is going to be reasonably valid, equal to 0. In other words, the centrifugal force has to be equal and opposite the centripetal force. Then have to add up the centripetal force. They have to add up to 0 in the rotating frame of reference. In other words, because remember that the centripetal force is actually a real force. This will serve as the centripetal force if you're at rest. And if there's no acceleration in the rotating frame, then the centripetal force and the centrifugal force have to add up to 0. That's what this equation says. So in spite of its somewhat complicated appearance, the centrifugal force can be understood simply as the minus of the centripetal force. And it's probably easier in most cases to work with this form rather than that form. So for that reason, I'm going to box these. Okay. And it's directed outward. Okay, so let's apply this in an interesting case here. And that is the case of freefall on planet Earth. Okay, so here's the Earth, and let's say we have some object here. Look at it at this point, and it's in free fall. In other words, it's falling down a mine shaft or something. The only real force that's acting on it then, if we neglect air resistance, is the force of gravity downward like this. Now, we also have, at the same time, the centrifugal force, which is going to be directed outward like this, away from the axis of rotation. So let's write down now what the total force, and the centrifugal force like this is something that we haven't taken into account before. So let's see what effect it actually has on the motion of this falling object. So Newton's second law now simply has this form. There's the gravitational force and the centrifugal force. So you're going to use that color coding. Oh, that was wrong. Like that. Okay. So the gravitational force and the centrifugal force. I'm going to combine them into a single force and just say that this is the total effective force that's acting on the falling object. This effective force, it's going to be, first of all, we have f of g. That's mg naught. That's what I'm going to call the magnitude of the gravitational force. We have that fg equals minus gm little m over r squared. That's the radius of the Earth, times r hat. That's the direction away from the center of the Earth. So write that as minus mg naught r hat. And I'm going to explain why I'm using g naught instead of g here in a second. Right. So this is mg naught r hat, and then we add in the centrifugal force. Now we can see here that this distance here is rho, but rho will just be the radius of the Earth times sine of theta. So theta is the co-latitude of the Earth. It goes from 0 degree at the North Pole to 90 degrees at the equator. So it's 90 degrees minus the normal latitude. So rho is r sine theta. So we can write then F effective in this manner. Now what we can see here is that this is actually just the mass times some constant, and that's it. It's just the mass times a constant vector. And that vector is not in the same direction as r hat, but it has the same effect on the falling object. It pulls it in a straight line. It accelerates it in a straight line. Where this term here acts as a small correction. So let's see how small that correction is. So let's take this net force here, this F effective, and divide into a radial component and a tangential component. So first we're going to have to note here that rho hat scalar r hat, that's sine of theta. So that means if I take F effective, let's underline it here. We have F effective there, and we want to look at its direction in the radial, its magnitude in the radial direction. That's F effective scalar r hat. That is a minus mg naught plus m omega squared. Then we have the rho, which is r sine theta. And then we have another sine from there. So it's actually sine squared theta. And we can write that as minus m g radial. So g radial is therefore g naught minus omega squared r sine squared theta. So this is the magnitude of the effective g in the downward direction towards the center of the Earth. Now note that we can't really tell the difference between this effective radial acceleration and the acceleration due to gravity. The reason is that the centrifugal part of the force is simply proportional to the mass, just like the actual gravitational force, and it just bundles together as a single object that actually determines the rate at which an object accelerates downward. So this is the downward acceleration in free fall. So we can see here that it varies with the latitude. So at the poles, the magnitude of g here, or the magnitude of g rad, it's almost the same thing, is the same as g naught. Whereas at the equator, g equals g naught minus omega squared r. So this is the angular velocity of the Earth. So 2 pi over 24 hours. The radius of the Earth, 6,400 kilometers. And we can actually calculate that relatively easily. If we do that, we find that it is 0.034 meters per second squared. That's not very large, but it is significant enough to be measured compared to this, which is on the order of 9.8 meters per second squared. In fact, the reason why we have that g at the equator is less than g at the poles is due to two reasons. One of them is this, that the centrifugal force at the equator is at its maximum value, and at the poles it's 0. And that accounts for about half the difference between the equator g and the pole g. And the other half comes from the fact that the Earth is actually slightly oblate, slightly flattened, which incidentally is also due to the centrifugal force. So that's a secondary effect, but both the secondary and the primary effect here pull in the same direction, and both are due to the centrifugal force, which makes gravity, or the effective gravity in any case, smaller at the equator than at the poles. So that's then, we look now at the radial component of G, we can look next at the tangential component of G. Well, if we take our F effective and take a scalar product with theta hat, that's the same as F effective in the theta direction. We can then make use of the fact that rho hat with scalar product with theta hat is cosine of theta. And then we get this expression from which we can extract that the tangential component of the effective G factor, the one that actually goes along the surface of the Earth, is omega squared r sine theta cosine theta. It has its maximum value when theta is 45 degrees. In that case, we can easily show that it's just omega squared r over 2. Okay, so that's the maximum value it has. Again, it's about the same order of magnitude as this. So it's really half the size of this, 0.017 meters per second squared. And from there we can relatively easily calculate the angle between the effective force and the direction to the center of the Earth. So we're going to say that phi is the angle between the true vertical, defined as the direction towards the Earth's center, and G, let's call it alpha. Alpha is equal to arctangent of G tangential divided by G radial. Now, because the tangential component is so much smaller than the radial, we can get rid of the arctangent. Arctangent of x small is approximately equal to x. Moreover, the radial component is completely dominated by G naught. So this is this. Omega squared r divided by 2 G naught. If you calculate that out, it becomes 0.0017 radians, or approximately 0.1 degree. So it's a very small angle. If you drop an object, it is not falling toward the center of the Earth. It's falling along a line that's about 0.1 degrees off from the center of the Earth. Now, it's very hard to measure this angle because vertical is really defined as a direction in which things fall. And that includes the effect of the centrifugal force. So in practice, measuring this distance is very difficult. It's much easier, though, to measure the difference between the magnitude of G at the equator and at the pole. And there we see a very easily detectable, relatively strong effect of the centrifugal force.